All right, so to begin our design, we will design a slingshot that can shoot a steel ball 50 meters. What's the components to the design? First, we'll use modeling to estimate the required exit velocity to achieve a 50-meter range with the slingshot. Second, we'll estimate the required elastic band stiffness to get that same 50-meter range. And finally, we'll design the slingshot geometry and specify the material using a computer-aided design software package. The first element of this modeling exercise is to estimate the required exit velocity to achieve 50-meter range. We're going to assume that we don't have to worry about air drag. Actually, from our last exercise, we can probably anticipate that air drag will be a factor in this kind of design, but we'll ignore it for this purpose. So we start with what we know about projectile motion again. If we have a velocity vector aiming off at an angle theta, then there's an x velocity and a y velocity initially, and we can write the particle velocity and displacement equations, velocity final in the x, velocity final in the y, position final in the x, and position final in the y as a function of those initial conditions and the accelerations in x and y. Well, for us, we know that the acceleration in x is 0 and the acceleration in y is gravity. So we get a set of constitutive equations that look like this. The final velocity in x is the same as the initial velocity in x. Final velocity in y is the initial velocity in y minus g times t. And then we get similar equations for x final and y final as a function of the initial conditions. These four equations have more than four unknowns, so we need to have some more information. And that piece of information that we'll use is we'll pick the angle of the slingshot. We'll let the slingshot shoot at 45 degrees. Why 45 degrees? Well, 45 degrees happens to be, in the absence of air damping and air drag, happens to be the angle at which the steel ball will travel the furthest. That maximum distance, finding out that that's 45 degrees, is a good calculus problem, but it's not one we're going to solve today. So at 45 degrees, the initial velocity in the y is the initial velocity times the sine of theta. And the initial velocity in the x is the initial velocity times the cosine of theta. And if theta is equal to 45 degrees, initial x velocity and the initial y velocity are 0.707 times v0. That simplifies those two equations up top. Also, we know that the initial x position is 0, and we'll say that we're holding the slingshot a meter above the ground, so the initial y position is 1 meter. The final y position when it hits the ground is 0, and the final x position, which is our specification, is 50 meters. Given those constraints, we can rewrite those equations of motion and velocity so that we know that the final x velocity is 0.71 times the initial x velocity, final y velocity is 0.71 times the initial velocity minus 9.8 times the time. And then we have these two lower equations, which are in terms of velocity and time, initial velocity and time. And we note that with those two bottom equations, we have two equations and two unknowns, so we can solve for initial velocity and time. In fact, when we do solve that, we find that the initial velocity is 22 meters per second, and the time is 3.2 seconds. Next, we estimate the required elastic band stiffness to achieve the velocity of 22 meters per second. This problem is a problem of converting potential energy into kinetic energy. Given that the spring of the elastic band has a stiffness K, we can find that the potential energy is K times the amount that we stretch the band squared over 2. Whereas the kinetic energy when the ball leaves the slingshot is mass of the ball times the velocity squared over 2. When we set these two things equal to each other, we get k delta x squared is equal to mv squared. And if we assume a reasonable pullback on the slingshot of 200 millimeters or 0.2 meters, we assume a 10 millimeter diameter steel ball, and we can calculate its mass by knowing the density of steel and the geometry of the ball, and we end up with a stiffness, K, of 51 newtons per meter. That solves the second part of the modeling problem. Now we have to design the slingshot geometry and specify the material so that we can achieve this velocity of 22 meters per second and this stiffness of 51 newtons per meter. To do that, we will use a CAD simulation software. The software we'll use is called SolidWorks.